Even when a set is not connected, we still tend to think of it as being made up of connected pieces. And well, that's what this definition of components is all about. Let X be a topological space, and let tilde C be the equivalence relation on X defined by a point X is going to be equivalent to a point Y if they lie in some connected subset of X. Okay, if you can find a connected subset of X that contains both of them. So in my picture here, X has sort of these three pieces, and well, the point X will be equivalent to point Y because there's this connected subset A of X which contains both X and Y. But X would not be equivalent to Y prime because there's no connected subset of X that contains both. And similarly, Y would not be equivalent to Y prime. All right, well, hopefully it makes sense that this is an equivalence relation. A point's equivalent to itself because if you look at the single point set containing just that point, that's always going to be connected. And if X is equivalent to Y, then you have connected subset A that contains both. And okay, well then it doesn't matter what order X and Y came in, right? If you had Y first and then X, there's still that same connected subset A that contains them. And then for transitivity, if you have X equivalent to Y and Y equivalent to some Z, then you have well, connected subset A containing X and Y, maybe B containing Y and Z. And well, those are two connected subsets that they overlap at least at Y, right? So their union is connected, and it contains, well, X, Y, and Z, but in particular it contains X and Z. Therefore, X and Z are equivalent. Okay. So it's an equivalence class, it's an equivalence relation, therefore we can talk about its equivalence classes, and that's what we're going to call components. Okay. So the equivalence class of X, remember, is just the set of everything equivalent to it. We can denote that by this X bracket, and in this case that would be A, right? And that's the same thing as the equivalence class of, that should just be a Y there. Let me see if I can, okay. Same thing as the equivalence class of Y, right? So that's the story. And we're going to try and prove the second part of theorem 6.12. Let X be topological space. If A is connected in X, then A is a subset of a component. Okay, that sort of makes sense because I mean these components, they're basically the sort of largest connected subsets of X that you can find. So if you have anything that's connected, it's got to be contained inside of one of these things. This sounds a little bit like a lemma that we used in a previous video, but well, it's slightly different because we're talking about components now and we didn't have that language before. Okay, well, let's go ahead and assume that A is connected in X, and I have to show A is a subset of a component. And remember, a component's an equivalence class of some point, right? So how about we take a point in A and look at the equivalence class of that point. So pick a point P in A. Okay, so there's P, and then I'm going to look at the equivalence class of P, which is bracket P, or I can call it C if I want to. I'm going to show that A is a subset of the component C of X given by, well, yeah, C is going to be the equivalence class of P, right, which by definition is the set of all X in X which are equivalent to P. All right. Well, why is A a subset of C? Let's take any point in A and show that it's an element of C. Okay, so indeed, every A in A, well, to be in C, you have to be equivalent to P. And every A in A is equivalent to P. Why? Well, since both points lie in the connected subset A of X, right? A is an A just because that's where I took it from, and P is an A because we picked P to be a point in A. All right, so they're both in this connected subset, and that's what it means for them to be equivalent. Okay, but if A is equivalent to P, then A is contained in its equivalence class. It's contained in C. So we've shown that every element of capital A is contained in C. Thus, A is a subset of C. And we're done.